I'd like to say that artists and scientists are communicators. They're storytellers, actually, and one of the things that we get to tell is nature's story. And my passion for science and art started at a very young age, but unfortunately, I came into the world being dyslexic, which was an obstacle in terms of learning, but it became an extraordinary opportunity in terms of how I see the world. And so for my presentation today, I'm going to share with you some of these unique visions that I've been able to do when I've combined art with science. When I look back on pivotal moments in my passion about science, one of the main things that I think about is an experience I had as a kid at the Franklin Institute in Philadelphia, walking through a human heart. Now, I know this might seem strange to many people in the audience because most of how you understand science in this day and age is through virtual animation. That was very different growing up when I grew up. So this experience of walking through an actual heart, the architecture of the heart, planted so many seeds of possibility of what science was about. Early tools of discovery for me were the microscope, and for many of you this might look like it's quite primitive, but it actually did the job. This ChemCraft chemistry set, which, believe it or not, you could not even sell today because the chemicals are so lethal. But the real magic for me of this chemistry set was being in the basement of my home in Philadelphia, and you always knew when science magic was happening because you could smell it. So smell became a really important aspect of chemical discovery. And then my personal favorite, which is a telescope that my dad and I built. It was actually built out of 2 paper towel tubes with some funky optics from Edmund Scientific Company, which was just across the river in Philadelphia. And I really believed it enabled me to see the cosmos, when in reality, all I could really see was across the street. But it didn't matter, because it planted that seed of scientific possibility. I've been very fortunate on my journey of discovery to be able to intersect with my work as an artist in many different kinds of scientific community. And the beauty about art is that art really provides a holistic way of looking at science. Many people that actually do science look at a very small part of a much larger puzzle. So I've been very fortunate in that I have been doing research at the top, up at the Center for Astrophysics at Harvard, and at the bottom in neuroscience at National Institute of Health. And in my world, and in my dyslexic brain, these two worlds are interconnected. And I'm going to share with you during this presentation some of these views. And I'm going to start with this first sculpture that is called Illumination. And it's one of the first pieces that was completed as a result of being in residency at National Institute of Health. It refers to this notion of the eye, that both the structure and the complexity of the eye, but it's created in such a way that it sort of is more abstract. It's nothing that you would probably find in a textbook on the human retina. But when it's shown to scientists, it enables them to view their research through a new lens. So let's talk a little bit about this notion of art and science, because in this day and age, it might seem very alien that you would bring together these two fields, when in reality, there's a long history of this intersection of art and science. Actually, before the advent of the first telescope, or I should say, before the advent of photography, scientists had to be artists. Why? Because they needed some kind of way to have to capture their data. And probably one of the greatest polymaths and scientists of all time is Leonardo da Vinci. And what you're seeing here are just composites of his worldview, of how he was able to use his gifts of art and really express a lot of his scientific findings. So you see the Mona Lisa, so it shows his ability to take a flat canvas and on that create this illusion of a person. And you also see his ability to dissect, which during the 15th century was something that was illegal to do, but he was able to do it anyway. He also was one of the fathers or the beginners of what we call linear perspective, which is taking a flat piece of paper and through the laws of perspective, creating this illusion of dimension. And then finally, he did a lot of investigation in terms of the worlds of physics and engineering, and truly looked at the world as an artist and a scientist extremely holistically. But what I want you to focus on here in the center is what's called the Truvia Man. And the Truvia Man deals with this notion that man is the measure of all things, that the human proportion really relates to proportions in all aspects of the universe. And that influenced this particular piece, which is now currently on view at National Institute of Health in their new neuroscience building. And what you see here are two waveforms. These waveforms relate to the actual use of sacred geometry to plot the human figure based on classical Greek sculpture. So this creates a waveform. And what's really interesting about this particular shape, it's also the shape of a harmonic in music. So you start seeing there's this interconnection of the visual arts to the science, to architecture, and to music. And what you're seeing here, these circular forms represent the percentages of water in the body and their relationship to the larger sea. So there is this dialogue between man and the ocean. And actually it was very interesting. I did a lecture up at NIH, and one of the neuroscientists said to me, that piece looks like constructive interference, which is a physics phenomenon. And I said, well, she said, what is the name of your sculpture? And I said, well, it's the measure of all things. And she said, that is constructive interference. So anyway, there is this wonderful marriage that happens when you bring the arts and sciences together. Another scientist who really was very passionate about their art was a biologist named Ernst Tausche. And what you're seeing here are some beautiful renderings he did of one-celled organisms called Radiolarium. Radiolarium are these just extraordinary creatures that live in the sea. They ingest sand and they excrete the sand to create these beautiful glass matrices, or their bodies. And in his lifetime, he actually identified over 4,000 species. This is back in the late 1800s. What was interesting about Haeckel, he became so involved in the representation of these just extremely beautiful forms that he literally gave up his biology career to become a full-time artist. He's also had a huge impact on the Art Nouveau movement. So now we have a scientist who has impacted the history of art. His work influenced this particular sculpture called Cellular Dialogue. And what it tells the story of is the cells in the body, which is represented here. This represents the water in the cell, and this is a very abstract version of actin. And its relationship to the larger seas or the larger ocean. And so you see this form here, and these red forms represent or an homage to Radiolarium. The thing that was very interesting to me, my mentor at NIH saw this piece and he looked at the coloration of this particular element, and he said it looked very much like missile stain. So one of the things that's so exciting to me in my dialogues with scientists is this opportunity to start seeing these relationships of ideas and forms that get to inform both our work. Another artist, or I should say another scientist who had an incredible passion for art was Santiago Ramon y Cajal. And I'm just curious, how many people in the room know Cajal's work? Well, let me just say, every single person in this room is impacted by his Nobel Prize-winning discovery of neurons. So you have been greatly impacted by Cajal. Now, what's really significant about Cajal was he came into the world wanting to be an artist. His dad, who was a physician in Spain, said, no, there's just no way that's going to be happening. You have to be a physician like me. What you're seeing here on the bottom is an actual painting that Cajal did when he was 8 years old. And I had an opportunity to research in his archives, and part of my training is in sculpture, another part is in art education. My art education hat was put on, and I couldn't believe his ability to see and record at age 8 years old. It's pretty extraordinary. So when you look at this, you understand how someone who can see and record that much when they're 8 made the prize-winning discovery of neurons and the significance of neurons in the brain. His research influenced this sculpture that I've created called Butterflies of the Soul, which is actually titled after a very famous quote of him talking about the neurons in the brain as a butterfly of the soul. And what this sculpture is doing is it's actually portraying the history of modern neuroscience. In the beginning, people thought that neurons were a reticulum, or a netting of cells. And what we see in the center is Cajal's contribution of a pyramidal cell, it wasn't a netting of cells. These were individual cells. These butterfly forms, again, relate to this notion of butterflies of the soul. These are actually inspired by looking at what are called Purkinje cells, which are certain cells in the brain. And these particular butterflies were inspired by a beautiful drawing of Cajal's Purkinje cells. What's really incredible, in his lifetime, he made over 7,000 drawings. I didn't get to look at all 7,000. That would have taken, probably half of my lifetime. But what was significant was knowing how significant drawing was in terms of his discovery, because he would spend hours looking through the microscope and he would be reproducing what he was seeing through drawing, as opposed to just taking a photograph like we do nowadays. That process of understanding through drawing was really significant to Cajal. In 2007, I was coming into my home after presenting a lecture in Santiago, Chile, and I had this vision of the periodic table of elements. At first I thought jet lag, bad food. I mean, who gets this notion of the periodic table of elements? So what I realized that I was supposed to do something with this Mendeleev classification of elements, to take this rigid chart that we've all glared at in high school. You can fess up, I'm sure, like me, you had that experience, and try to make it interactive and compelling and beautiful so people would want to learn more about chemistry. So what I did is I focused on one aspect of the elements, which are the orbital patterns, which are considered to be one of the most ethereal parts of the elements. And what I did is I created sculptures based on each of the 83 naturally occurring orbital patterns for the elements. And what I wanted to do is I wanted to take that rigid gridded chart off the wall, and I wanted to make it interactive so people could walk through it and find it as beautiful as my research revealed when I was studying it. Because my research took me all the way back to the beginning of chemistry, dealing with alchemy. So what you're seeing here is a sculpture installation that is laid out on a Fibonacci spiral, which is just a traditional spiral that we find in all aspects of nature. But there was another special component to this. It had a sound component. And I do a lot of collaboration on these big installations with a wonderful sound artist in Portland, Oregon, named Susan Alexander. And she was investigating what I was, but through sound. And so you were actually hearing sound that was being translated from data coming from each of these elements into audible sound. So you walk through it, just like a garden, and the idea was that it would reveal aspects about the periodic table. So then I thought, everything's better with dance. Bring in the dancers. So what I did was I invited a local dance troupe to come in and to interpret the periodic table using the installation as a set, and also using the soundscape as the sound component for it. And it was really exciting because I don't think anyone that experienced this will ever think about the periodic table in the same way. Then one day I got a very interesting phone call. Someone called me and said, if you're willing to do a lecture on your work, I'll let you hold Einstein Spring. How can you say no to that? That's probably one of the most extraordinary things I've held in my hands. And you know, I deal with a lot of scientific archives. This really was. And so as I was examining, it wasn't his real brain, it was actually histological slides of his brain. As I was looking at these slides in the palm of my hand, and this is one example of it, I was wondering how the uniqueness of his brain, the inner space, impacted his view of outer space. So, my research uncovered two major things. One is he had more folds in his brain than mere mortals like us. And the other thing was that he had an inordinate amount of what we call glial cells, which are cells that sort of hold neurons together, in the thinking part of his brain. And so the glial cells clear away things, you know, debris, so that lets more thoughts flow. So this is actually a piece that was created called Glial that was inspired by the fact that this was a significant aspect of Einstein Spring and ours. So a current project, which has really been very important to me, this is the International Year of Light. And it also relates to the fact that it's also the centennial of Einstein's discovery of general relativity. And for anyone who's an Einstein fan like me, this is a very significant year. So I use this as an opportunity and an invitation to understand and to try to portray in a very poetic way general relativity. As you can tell by now, I like to take on the weighty scientific problems. And if you think it's difficult to solve it scientifically, you should try trying to solve it poetically. So what I decided to focus on were the orbital patterns, and you're probably noticing by now that I'm very passionate about patterns, and patterns are one of the things that connects art and science. And so what you're seeing here is a very beautiful visualization of two binary stars orbiting. And this particular visualization was done by a group of astrophysicists who I have collaborated with at the Rochester Institute of Technology. And so what I've created is an interpretation of my understanding from dialogues with astrophysicists at Harvard, MIT, and RIT about the aspect of general relativity. So what we're seeing here, these conical shapes are cut out. They're about 3 feet by 3 feet. They're all cut out by hand. And what they're trying to do is communicate the patterns, these chaotic patterns that are created by orbiting black holes. And since they're cut out flat, when I hold them at one point, like you see hanging here, gravity, which is the same thing that they're representing, actually hold it in this particular formation. So each one of these is a representation of two binary stars that are orbiting very quickly and very chaotically. When that happens, that movement creates what we call a wave. And it's these waves now that astrophysicists are able to start investigating through lasers. And actually, Einstein, very interestingly, had done a lot of research on laser technology. Now, in the center of each one of these is a beautiful fossil, and the fossil represents the notion of geological time and its relationship to space-time. If anyone's interested, this particular installation is on view right now at the National Academy of Sciences through July 6th as part of this big Einstein Centennial. So you'll be able to see a portion of it. This is a much smaller version of the larger portion, or of the larger installation. And then I'd like to end my talk with these three images. And this was an experience that happened. My neuroscience mentor at NIH had come over to see the portal installation, which is the gravitational wave installation. And he was really quite taken by the fact that this conical form that I created to describe binary orbiting black holes was really similar to a form that I had created based on a neuroscience phenomena called growth cones, which is something that Cajal had discovered and is this very interesting form at the end of neurons that reaches outward. And so what was really exciting to me was how I could create a piece of artwork that enabled a colleague in neuroscience to try to understand how it related to research being done in neuroscience. But then it gets better, because last week I was invited to do a lecture up at the Center for Astrophysics at Harvard, and I showed them this particular image, and it created such a wonderful dialogue. So as an artist, it's so humbling to be able to create work that interprets different scientific fields and to be able to use it as a catalog for a dialogue and a bridging between very, very diverse scientific fields. And then finally, a project, because of my own enthusiasm about scientific discovery, this is a project that connects me to George Mason University. Several years ago, I created an art challenge for the Science Summer Intern Program at GMU. And what I did was I challenged summer science interns to interpret their research using art. And this is one example. These are two women that were researching the hippocampus area in the brain, and since that deals with spatial relationships, they interpreted it in deep space, in outer space, as a new constellation that was actually based on the shape of the hippocampus. And so we got wonderful feedback from students that were part of this art challenge, because it enabled them to understand their science in new and more innovative ways. So this is something that I've gotten to do that has enabled me to extend my own art practice and my own enthusiasm about discovery to young scientists. So finally, I want to end with this notion of what happens when you add art to science, technology, engineering, and math. Truly, the sky's the limit. And it's an idea we're sharing. Thank you very much.